right, moving on to section 3.9, there are two topics in here that we're going to look at. The book treats them kind of in a similar way. We're really just going to deal with them as two separate ideas, important for very different reasons. The first is the idea of a linearization, and then we'll talk about these things called differentials. We're going to start by talking about this thing called a linearization. And linearization is really just a fancy name for tangent line. But there's a little bit more to it than that. Let's say I have some function, f of x, and draw in the tangent line at a particular x value, maybe like x equals c. So I've got a tangent line right over there. I'm going to call the tangent line L of x, my linearization. The point is, I can use my tangent line. Notice, well, hold on, before I say that. Notice that when we're pretty close to x equals c, that tangent line is really close to my function f of x, which means I can use my tangent line to approximate my function for x values that are very close to x equals c. Let me write down some of these ideas. Given a function f of x, and a point on the function, I'm going to call that point c comma f of c, we can create a linearization L of x, which again is just a tangent line, that approximates f of x when we're pretty close to x equals c. Given a function f of x and some point c comma f of c, we can create a linearization, I'll call it L of x, our tangent line, that approximates my function when we're pretty close to x equals c. Take a moment, get all that stuff copied down. I want to try to write a formula for my linearization. And I know it's a tangent line, so I'm just going to say y minus y1 equals m times x minus x1. Well, x1, that's c, and y1 is f of c, and my slope, I always get the slope from my derivative, so I'm going to make my slope f prime of c. So y minus f of c equals f prime of c times x minus c. I want to try to solve this thing for y. So I can say y equals f prime of c times x minus c plus f of c, or L of x equals f prime of c times x minus c plus f of c. And this is my formula for a linearization. This is not a formula that's going to be worth memorizing. The formula worth memorizing is y minus y1 equals m times x minus x1. But I'm going to show you in a moment how we can kind of basically use this formula to do some approximations of functions. But make sure you get everything copied down first. Okay, let me show you what we can do with this. If f of x equals the square root of x, let us create a linearization at x equals 1. When we're done, we're going to use it to approximate the square root of 1.1, and the square root of 1.2. We're going to consider the function f of x equals the square root of x. I want to create a linearization at x equals 1. Got my square root function. I want to create the equation of a line tangent at x equals 1. My equation is y minus y1 equals m times x minus x1. x1 is 1. y1, I need to plug into my original function, so I'll find f of 1. And m, I need to plug 1 into the derivative. I need to find f prime of 1. Take a moment and go write your equation of a tangent line. Then we're going to do a tiny bit of easy algebra to turn into a linearization, and then we'll do our approximations. But right now, go get your tangent line in y minus y1 equals m times x minus x1 form. Before I do this, I do need my derivative. F prime of x is going to equal 1/2 x to the negative 1/2, or 1 over 2 root x. F of 1 is the square root of 1, that's 1. F prime of 1, 1 over 2 root 1, 1/2. My tangent line is looking like y minus 1 equals 1/2 times x minus 1. To turn it into a linearization, all I'm going to do now is add 1 and replace the y with an L of x. My linearization is L of x equals 1/2 times x minus 1 plus 1. That is my linearization. I don't want to distribute the 1/2. You'll see why in a moment. If I want to approximate the square root of 1.1, well, it's like I'm going to plug 1.1 into this function over here to get the actual value of the square root of 1.1. So I'm going to plug 1.1 into my linearization to get an approximation. The linearization at 1.1 is going to equal, and again, this is just an approximation that I'm using. The linearization tells me 1/2 times 1.1 minus 1 plus 1. I can do this without a calculator, I think. 1.1 minus 1, that's 0.1. I want to do 1/2 of 0.1 plus 1. 1/2 of 0.1, that's 0.05 plus 1. I'm getting an approximation of about 1.05. Let me compare this to the actual value of the square root of 1.1, which would really just mean plugging 1.1 into my original function. This will give me my real value. F of 1.1 is the square root of 1.1, which I can't do by hand. Let's go to the calculator for that. Square root of 1.1. Type it in. When I do that, I'm getting about 1.0488. Yeah, that's pretty close to 1.05. This would be an absolute pain, though, to do by hand. This is a whole lot easier. And that's sort of the point, is linearizations give us a much more computationally easy approximation of values that are kind of difficult to figure out by hand otherwise. What if I want to approximate the square root of 1.2, which means plugging 1.2 into the linearization? See if you can do that by hand. No calculator for this. So that's 1/2 times, okay, 1.2 minus 1 is 0.2, plus 1/2 of 0.2 is 0.1, plus 1, this is 1.1. That's my approximation. To find the actual value, I'll plug 1.2 into my original function, which is just my square root of 1.2. Go into the calculator, that's about 1.0954. Yeah, that's still a pretty good approximation. I think this one was better than this one because, well, when you're pretty close to 1, the further away you get from 1, the further away those things differ. The distance between them is really the difference between our approximation and our actual value. So because 1.1, 1.2, when we're at 1.2, the difference between them is greater, our approximation is not quite as good. And I guess if we go all the way to x equals 2, well, my linearization is really not going to be a great approximation for the square root of 2. Further away we go from that point where we create our tangent line, the worse our approximations. I'll give you a moment to get caught up on writing stuff down. Next thing. I want to be able to figure out, without knowing actual values, if my linearization is an overestimate or an underestimate. Overestimates and underestimates. For the linearization, at x equals c. I want to figure out if my approximation ends up being an overestimate or an underestimate. And it's actually not going to matter what my specific value I'm approximating it is. It has more to do with the shape of my function and where the tangent line is. If the second derivative at that particular x value is positive, if the second derivative is positive, what does that mean about the shape of my function at x equals c? Am I increasing? Am I decreasing? Am I concave up, concave down? Second derivative being positive means I'm concave up. Okay, watch this. No matter where I am on a concave up shape, there's a tangent line, there's a tangent line, there's a tangent line. My tangent lines are always below my function. Therefore, our linearization will give us an underestimate. Our linearization gives an underestimate. Similarly, if f double prime at c is negative, meaning I'm concave down, tangent lines here would all end up going above the function, so our linearization gives an overestimate. Our linearization gives an overestimate. Take a moment and get those two copied down. I have a hard time remembering these two things, so really I don't remember the rule. I just sort of draw it out and kind of figure it out. I draw a concave up shape, draw on my tangent line, see that they're below, draw a concave down shape, draw the tangent line, see they're above. All we really need to know is to determine overestimates and underestimates, I need to look at my second derivative and need to think about concavity. Let's take a look at an example of this. We're going to use a linearization to approximate (1.99) raised to the fourth power. We are going to determine if it is an overestimate or an underestimate. And we're going to justify our answer. Please take a moment and copy that down. So first of all, to approximate this thing, it's kind of like I'm looking at my function x to the fourth, And I'll find a linearization to that. We're going to say let f of x equals x to the fourth, and we're going to use a linearization at, well, 1.99 is really close to x equals 2. I'm going to do my linearization at x equals 2. How about you take a moment, you go create your tangent line, and then stop. I know I'm going to need my derivative, so I might as well go find that over here. My derivative is 4x cubed. My tangent line is y minus y1 equals m times x minus x1. x1's 2. y1 is f of 2, which is 2 to the fourth, which is 16. m is f prime of 2, which is 4 times 2 to the third, 4 times 8, 32. So I think the tangent line should be y minus 16 equals 32 times x minus 2. I'm going to go and turn this tangent line into a linearization by adding 16, just replacing the y with an L of x. So I'm going to say L of x equals 32 times x minus 2 plus 16. I now want to use this to approximate 1.99 to the fourth, which means all you need to do is plug in 1.99. See if you can go through those calculations without a calculator. Well, 1.99 minus 2 is negative 0.01. That is negative 0.32 plus 16. $16 minus 32 cents is going to give me 15.68, I believe. I want to figure out if this is an overestimate or an underestimate now, which means we need to go look at the second derivative. F double prime of x is going to equal 12x squared. I'm going to plug in x equals 2. 12 times 2 squared, 12 times 4, 48. Well, am I concave up or am I concave down? I think I'm going to be concave up. So are my tangent lines, any sort of tangent line to something concave up, going to be overestimates or underestimates? Well, tangent line, oh, they're all underestimates. I am going to say it is an underestimate. Why? Because f double prime of 2 is positive. You know what, just for fun, let's find the actual value of 1.99 to the fourth and compare it to our approximation to make sure our approximation really was an underestimate for the actual value. 1.99 to the fourth is going to be a pain by hand, although you could do it. 1.99 times 1.99, multiply that answer by itself by hand. Take a moment, go to your calculator, and let's get the actual value. I am getting an actual value of about, let's see, 1.99 to the fourth, getting about 15.68239.201. Actually, this is a really good estimate of that. But yeah, this is a little bit lower than the actual value. So yeah, my justification worked. That is an underestimate.